All right, so after much anticipation, I'm assuming, we are finally at a point where we can start to discuss logarithms. So we've been talking about exponential functions leading up to this, and maybe you're wondering, what do logs have to do with exponents? Well, there's a lot. There's a lot that they have in common. So that's where we're going to start. We're talking about what is the connection between a logarithm and an exponential function. So I'm going to start right here with the definition. I just want to write the definition out. So as you're asked, what is a logarithm? A logarithm it's the inverse function, or the inverse of an exponential function. This is extremely important to know and understand, because all the properties we're going to be using and learning about logarithms are all related to exponential properties. So if you know the exponential properties, then that's going to assist you in learning about log properties. And if you don't remember what an exponential function is, well, this is an exponential function. So it's y equals b to the x. Well, the inverse of that function is where you take the x and y values and you switch their places. So it's x equals b to the y. So the problem is, though, if you wonder why we create this thing called a log, well, normally what you would do if you were trying to find the inverse of this guy, of this function, you would take this and solve it for y. And if you kind of notice here, if you tried to solve that for y, you might have some problems, because it's kind of hard to get that y out of the exponent. So you have to create some new math, or at least some math that we haven't learned about yet. So that's where logarithms come into play. Now I'm not ready to just kind of show you all these properties. I'd be kind of doing 3 lessons at once. But we're going to learn about these properties of logs, and then what we'll be able to do is use those skills, those properties, once we've created this new type of function and kind of studied it and analyzed it. We'll be able to solve these equations where the y, or whatever it is you're trying to solve for, is up in that variable. So with the variables and the way they're associated, you can see you can kind of go two directions with this. You can say that the log is the inverse of the exponent, or you can say that the exponential function is the inverse of the log function, because it can go both ways. You can write your exponential, or your function as a log, and by the way, this logarithm, I guess I need to state that while I'm here. This logarithm, I know it's in the box to the right here, but I'm just trying to make a connection between all three. I know I'm moving the stuff around a lot. Sorry. So what we do with this logarithm is we write it in this form. We say that it is y equals log base b of x. So when you solve for y, obviously to get from this step to this step, you're going to have to do some math that you haven't learned yet. So I'm not ready to throw that at you, because I feel that would just scare people. But that's what we're going to have to learn how to do. So we have to start studying the logarithms, understanding, again, where they come from, because that helps you kind of create a lot of these properties. But then we're going to get to a point where we can solve these equations. And there's a lot of applications that we can do with them as well, which we'll be doing towards the end of this unit. So kind of taking all this information and just looking here, there is a connection, a quick connection if you need to go from logarithms to exponents. Just by definition, we can jump back and forth rather easily. So if you had a log, and these variables are a little different, don't let that scare you if it's an x or an a or a b or whatever. It's still going to have the following property. It's an inverse. So the base is the base. The log base b, which is how this is read, log base b, of a, it is a function, and that is your input, equals x. So in this case, that x is the output. But again, you can change those variables just like you can in any functions. You can have linear functions that are in terms of b and l, or m and n and c and whatever. So variables are variables. They can be changed quite a bit. But in this case, we have log base b. So when you're writing your exponential form, the base of the exponent is also b. From there, it is an inverse. So be aware that the output of the log, this is your output. Notice it equals this. that becomes the input of your exponential form. So now it's to the x power, and that equals, so when you say what does it equal? Well, the input of the logarithm becomes the output of the exponent. So again, the input and outputs switch places. So what we're going to do is practice a couple of these, and I'm going to keep repeating that same idea, that thought process. So when I come down to number 3, we're going to do this again. I want you to look at this logarithm and notice this 1 is your input. This 0 is your output. I want you to write this, you can see the directions. We're going to convert these to exponential form. So the way you do that, you write your base, which is 7. Be aware that the output of the logarithm is going to become the input of the exponential function. So the output becomes the input. And the input, because we're writing an inverse function, the input will become the output. As you're doing these, on the homework and any quiz that we take as well, obviously the exponential function should be a true statement. 7 to the 0 power does equal 1. If you accidentally did 7 to the first, well, 7 to the first doesn't equal 0. So there's some ways to kind of check yourself here as well. All right, coming down, let's do number 4. So this one, write that as an exponential function. So as you write this, you're going to have your base, which is 2. And that base is, and again, you got to remember, this is your input, and this is your output. So the output becomes the input. So you get 2 to the 4th power. The input becomes the output of your exponential function. Do you have a true statement? Yes, you do, so you're good. And it's nice to be able to check these statements right now. When you get variables in here as you're solving, you're not going to know that. So you're going to have to get used to it now before you have to solve equations. But there we go. And then number 6, same difference. So this will be 9, that's your base, to the 3/2 power, because your output was 3/2, so that now becomes your input, and that equals 27. And again, if you know your properties of radicals, you'll know that that is a true statement, because maybe you don't remember your properties of radicals. This is the square root of 9 cubed, so I'm going to write it as 9 squared times 9. Okay, it's a square root. So if you take the square root of 9 squared times the square root of 9, the square root of 9 squared is 9. And the square root of 9 itself, by itself, is 3. So you get 27. So it does work. So obviously it should work. But I'm just kind of showing you how you can still test that. So that's converting from logs to exponents. What about if you do exponents to logs? Well, it's the same thing. Obviously you're writing logarithms now, but it's the same thought process. The base of the exponent is the base of the log. So on number 7, I'm going to write the log base 14. Okay, so that's your base. Now, remember you have an input and you have an output. The input of the log is now comes from the output of the exponential function. So that'd be 196. The output of the log comes from the input of the exponential function, which is 2. There's number 7. Moving on, number 11. A few things you have to know for this one. You got your log. I'm going to zoom in now on that. So you got your log. Remember, your base is going to be the same as the base of the exponent, so it's still log base 2. But remember now, the input and the output are switched, so this becomes log base 2 of 1/8, because that was the output, now it's the input, and that equals -3, because the input becomes the output. So that's number 11. Number 12. Do this one real quick. We got log base 8, because the bases stay the same, and the output and the input switch places, so that's 16, and that's 4/3. Again, the output is now the input's now the output. You're just switching places. And always kind of remember that. If you do think of it that way too, you also hopefully don't forget that these are just inverses, because that's what an inverse does. So it kind of helps you remember that whole concept of inverses if you kind of walk through it that way. All right, so that is exponents and logs. There are some properties and some special types of logs that we're going to learn about, and it's just a process of learning all these things. I'm just going to do one at a time, and the first thing we're going to learn about is going to be your common logs. And to set this up, I want to show you your calculator, and I want to focus at this point on one particular value here. So if you're looking at these values on your calculator, you kind of follow my mouse here. You have this button right here that's a log. It says log. You also see if you hit second, it's 10 to the x. This log right here is called your common log. There's another one right down here called natural log. When we move forward a little bit, we'll talk about that one. Right now, we're just talking about this log button right here. And it is called a common log, and it is a log base 10. So what we do is when we want to work with a log base 10, you don't have to write the base. Just like with square roots, you don't have to write the 2 if it's a square root. This is your common log. And the reason why this is the common log is, well, you know, we have a 10 base number system. So our numbers repeat every 10 units. So this is a pretty good number to use for our common log. I love the natural log, the log base E that we'll learn about later. That's my favorite. But this one is also very useful. So anyway, be aware if you see something like number 15 is asking right now, by the way, these problems are asking us to actually evaluate. So I want to know, what does this log equal? Okay, so when we do number 15, I'm saying evaluate each log. You have to look at this and say, well, where's the base? Well, the base is 10. Okay, that's the base. So in order to solve this, we need to be able to rewrite it as an exponent. But now we know the base is 10, so we use that common log to help us get there. So let's just give this output a variable. Let's call it A. I don't want to confuse you with x's and y's here, so we'll just call it A. So if you're going to do this, remember we're going to write it as an exponent. Remember the base is the base. And now the output of the log becomes the input of the exponent. So 10 to the A power equals 100. And then you just have to ask yourself, or you break down the bases so they're equal, but this one's simple enough. You can ask yourself 10 to the what power is 100? The other option is to do this, 10 to the A equals, and 100 is 10 squared. Oh, look, A is 2. Or you just know that A is 2 because it's kind of a simple one. But again, you can't do that one if you don't understand that a common log doesn't have that 10 written on the bottom. You have to realize if it's missing, it is a 10. All right, so that's number 15. Number 16, we're going to do the same thing here. We are going to rewrite this. I'm going to call that A again, just to give it a variable. And we're going to go 12 to the A power equals 1. Remember, the output and the input switch places. And then you got to, again, know your exponent properties. Any number to what power equals 1? Well, in that case, that's going to be 0. So A to the 12 to the 0 is 1, so A equals 0. So again, you have to use some exponent rules, obviously, as you do some of these. And then we have 19. Just kind of now reviewing a little bit of what we just did in the prior unit. Remember, we'll call this A. So we're going to go 9 to the A power equals 81. So again, as you're doing this one, you ask yourself, geez, 9 to what power is 81? Or you say, well, let me just break this down so that they have the same base on both sides of the equation. So, oh yeah, it looks like A is 2. All right, so that's going to be number 19. And then number 20. So number 20, first off, you want to set this up. It's a 64. That's your base. To the A power equals 4. Input and output switch places. So as you're solving this, you got to ask yourself, what base do they have in common? If you don't know what it is, just go ahead and start breaking this down. So this is going to be 8 times 8. 8 is going to be 2 cubed. and 2 cubed. So it looks like if I was going to rewrite this, this is going to be 2 to the 6th raised to the a power. It's just 2 times 2 times 2 and then 2 times 2 times 2. That's how you're going to get 64. Equals 2 to the 2nd power. So at this point, you can do that. You also, I just noticed it here, I didn't even have to break it down to the 4s. But this would work. I'll show that since I already wrote it. That's 2 to the 6a equals 2 squared, which ends up equaling 6a equals 2. I'll show you I could have done it with the base 4. But a, if you simplify this, is 1/3. So I broke it down to base 2. I didn't have to. I see it now. I just was focused on breaking it down to a 2. But if you look at this, again, it doesn't matter. So if I did it with base 4, again, if you look at these numbers right here, this would be 8 times 8 is actually 4 times 2 and then 4 times 2. Combine these, and 4 cubed is equal to 64 as well. There's a couple ways to get to 64. So I could have gone 4 cubed raised to the a power equals 4 to the 1st. So 4 to the 3a equals 4 to the 1st. And obviously if you solve that, you're also going to get 1/3. So it's just a couple ways you could have done that. Obviously they both work. So you break it down so they have the same base and just solve it whatever method or whatever base you're wanting to get it down to is fine. Okay? And it's just adding that one step in there, obviously. But that moves us on to our next part here, and that's going to be on the change of base formula. So again, I'm just adding in little concepts and things about logs as we move forward here. So the next one is going to be our change of base formula, and that's going to be useful, and this is where we start using our calculator. The only bases we have on our calculator are log base 10 and log base e, which is natural log. We've only talked about log base 10 at this point, so we're going to use that one. So the change of base formula looks like this. So if you have log base b of a, obviously that b is going to be a nasty base. In other words, it's not 10 and it's not that e number that we haven't talked about. When that occurs, we're going to use this change of base formula, which is log, and you can make this base any base that you want, not 0. I'm just saying, but again, I'm going to use base 10. Because I'm using base 10, I don't have to write base 10. So it's going to be, I'll just call it log A divided by log B. As I said, this formula actually works. You can use any base you want for that base. But because your calculator only uses log base 10 or log base E, those are the only two bases we'll more than likely be changing our logs into. There's really no other reason to use another one. So right now we're just going to use log, common log, log A, log B. We will use natural log when we get there. So anyway, with this, if I was going to use my calculator to evaluate these logs, again, I couldn't always just write this. If I was trying to do it this way, don't write this down. But I just want to show you what I'm doing. If I went 16 to the a equals 64. If you have a nice answer and you can break these down, then obviously we can go ahead and do that. So this would be, if you look, this would be 4 squared to the a power, so that's 4 to the 2a. And I think we just discussed, literally like right up here, 64, that's going to be 4 cubed. So when you get this, and these bases are equal, you're fine. You can go 2a equals 3, and I'm doing just fine. I can find a. But I also want you to see this. You can also solve it using your change of base formula. Now it does involve using the calculator, but we can just go this route. So look at your change of base formula as I write this out, but it's going to be log base 10, so I'm not going to write the 10, log of 64 divided by log of 16. And you're going to bust your calculator out at this point. So you're going to go log 64 divided by log 16. Of course, I should probably write it correctly. That would be good. Log 16. Okay, so plug that in and you get, look at that, that's 3/2. So you get the same answer as you are solving this. I should probably, you can't see all of that, I'm sure, on my screen. If I try to move that, it doesn't really work. So basically I plugged it in on my calculator, but I can't get this to work. I don't know if that's going to help you see it. It doesn't. I can hopefully move, I can't move it down. So basically I plugged it in my calculator. You can't see it, unfortunately. I'm sorry, because it's cutting off the top of my screen. But you just plug that in your calculator using that log button that I mentioned right here, and it should give you that answer that barely blipped down on the screen there. So you just plug it in your calculator, you're going to get 3/2. Alright, so got two more to kind of wrap up and then we're done. So the final two that we got a log base 10. So this one, if you were going to do a change of base, again, understand you can have the same base and still use change of base, but at the same time, if it's log base 10, you can plug that right into your calculator. So I just want to show you how those are basically the same. You'll see if I go log, I'm doing the change of base formula, I can go log of 294 divided by log of 10. Well, you have to understand, what is the log of 10? Well, the log of 10, this is base 10, you would say log base 10 of 10 equals what? Well, 10 to the a power equals 10. For you writing it as an exponent, if you look, oh wait, a is 1. So this really goes away. You can apply the change of base formula, just understand you're dividing by 1, so there's really no point in doing it. And that's the whole point. It's like we have a log base 10 on our calculator. So if I was going to solve this, I'm just going to plug it in as the log of 294 on my calculator. So if you want to use the change of base formula on that, you're not going to be wrong. It's just there's no point in doing it. Again, you can't see the top part of my calculator. I apologize for that. I can't. Maybe if I type a bunch of stuff in, yeah, I think you can see it now. Okay, so anyway, I'm going to hit log of 294. And again, I don't have to divide that by log of 10 because that's just dividing by 1. So you plug that in, you get about 2.468. So again, you don't always get pretty answers, just like with any other function. You think 10 to what power is 294? Well, not a pretty number, so that's going to be 2.468. And then 26. So here, this is another one we can solve without a calculator or with a calculator, but I want to show again the change of base formula is useful. Like I said, it can be useful in a lot of different scenarios. So if I was doing this one, you can literally just go common log of 1 over 36 divided by common log of 6. So again, this goes in your numerator, and the base is the input for your denominator. That's your change of base formula. So if you're plugging this in, same thing as before, we're going to go log of 1 over 36 divided by log of 6. And this gives you -2. You're not sure, it's like, wow, that's a pretty nice number. It's because it can be solved. Again, I'm giving you some that can be solved by hand as well, so you can kind of see the comparison here. But the whole point with the common logs is, it can solve those nasty ones, the ones that aren't pretty as well. But if I wrote this one as be 6 to the a power equals 1 over 36. So if you're going to solve this, you would just say 6 to the a, 36, you move it to the top, it becomes 6 to the -2. You can see how that would get you your answer. So again, the whole use of the change of base formula is it'll solve all problems, whether they have nice looking answers or really, really, really ugly answers. It'll always work. And again, there are times you need a calculator because your answers are irrational solutions, and you're not going to be able to do those in your head. So these are some skills you're going to need. So you can go ahead and do your homework on this now, and I'll see you guys back in class next time.